I'm going to discuss question 7 for my CPR credit. Similar to the method of finding the electric flux density field, the magnetic flux density field, or B, is the magnetic flux per unit square. If we want to find the electric flux going through a surface, we can integrate d dot ds over the surface. Similarly, if we want to find the magnetic flux going through a surface, we can integrate b dot ds over the surface. Suppose we have a closed Gaussian surface as shown. If we integrate b dot ds through the magnetic flux line, we can observe that because the magnetic flux line closed on itself, the leaving magnetic flux must re-enter the Gaussian surface, which makes the sum of the magnetic flux equals to 0. Therefore, the integral of b dot ds through a closed surface also equals to 0, which is the fourth Maxwell's equation. Next, I'm going to talk about magnetization. Along a current flowing wire, we know that current generates magnetic field. These currents are called free current. Inside a material, we have the electrons orbiting around atoms, which is known as the bound current, and generates a new magnetic field called the magnetization. In the case of electric field, we know that free charge generates electric flux density field, and inside a material there's a bound charge generating polarization field. So we can treat the electric field intensity is coming both from free and bound charges. We can treat the magnetic field in a similar way that free current generates magnetic flux density field, and inside a material there's a bound current generating magnetization. So we can treat the magnetic density field is coming both from free and bound current. We know that free current generates magnetic field intensity, and the relationship between magnetic field intensity and magnetic flux density field is B equals to the permeability of free space, or mu0 times H. We also know that bound current generates magnetization, which also generates magnetic flux density field, so we can say B equals to mu0 times N. By putting both equations together, we found that B equals to mu0 times the sum of H plus M. By now we have learned that the integral of b dot ds through a closed surface equals to 0, and the magnetic flux density field is equal to the mu0 multiplied by the sum of the magnetic field intensity and the magnetization. If we substitute b into the integral, we can find that the integral of h dot ds around a closed surface is equal to the negative of the integral of m dot ds over the same closed surface. With this information, we can start solving our problem. In this problem, we have a bar with a magnetization of m in the x direction, and we are asked to find the integral of m dot ds or integral of h dot ds in the three Gaussian surfaces. We are also given that the integral of m dot ds in the Gaussian surface 1 is negative 6 amp meter. To start this problem, we can start by determining the direction of the magnetization. Given that the integral of m dot ds in the Gaussian surface 1 is negative 6 amp meter, we can know that the magnetization is pointing in the negative x direction because of the minus sign. So the magnetization must be pointing in the opposite direction of ds. Next, we need to find the integral of m dot ds of the Gaussian surface 2. Notice that the magnetization that enters will leave in Gaussian surface 2. So the integral of m dot ds is equal to 0. Next, we need to find the integral of h dot ds in Gaussian surface 3. We can start by finding the integral of m dot ds in the Gaussian surface. Because the magnetization is pointing in the same direction with ds, we can find that the integral of m dot ds in Gaussian surface 3 is 6 amp meter. To find the integral of h dot ds, we can use the equation we learned earlier to find the result, which is negative 6 amp meter. We know that the integral of h dot ds must be negative because everywhere the magnetic field intensity is coming into the Gaussian surface. Lastly, we want to find the magnetization of the bar. Given that the integral of m dot ds in the Gaussian surface 1 is negative 6 amp meter, we can find the magnetization by solving for the integral. which will be m multiplied by the cross-sectional area of the bar. After plugging in the value of the area, we can find that the magnetization is equal to -2 m per meter in the x direction.